Section 430 of the National Electrical Code does not provide explicit guidance for sizing conductors for motor circuits operating above 2300 volts. In such cases, it is best practice to consult with a qualified electrical engineer or refer to industry standards and recommendations. The minimum motor amps used for conductor sizing are typically based on the maximum current drawn by the motor, which can vary depending on the voltage and motor characteristics. For voltages above 2300 volts, the motor amps may be significantly lower than the values provided in Table 430.152 of the NEC. The Institute of Electrical and Electronics Engineers provides recommendations for sizing conductors for motor circuits in their publication IEEE Standard 141, Recommended Practice for Electric Power Distribution for Industrial Plants. The standard includes tables and equations for calculating minimum motor amps for voltages up to 34.5 kV. Another valuable resource is the manufacturer's data for the specific motor being used. Manufacturers typically provide recommended amperage values for their motors at various voltages. Here are some steps to consider. Firstly, consult with a qualified electrical engineer. Secondly, refer to IEEE Standard 141 for guidance. Thirdly, obtain manufacturer's data for the motor. Fourthly, use the information gathered to determine appropriate motor amps for conductor sizing. For a 4-pole 2500 horsepower motor operating at 4160 volts, IEEE Standard 141 recommends using a minimum of 900 amps for conductor sizing. When dealing with motor installations operating above 2300 volts, several critical factors must be considered to ensure safety, reliability, and code compliance. Firstly, the National Electrical Code, while comprehensive, doesn't explicitly address conductor sizing for motors exceeding 2300 volts. This necessitates a deeper dive into industry standards and best practices. Secondly, understanding motor characteristics is paramount. The motor's horsepower, voltage rating, and full load amperage are crucial for proper conductor selection. Always refer to the motor's nameplate for accurate specifications. Thirdly, IEEE Standard 141 serves as a valuable resource, offering guidance on power distribution for industrial plants. It provides equations and tables for calculating conductor sizes based on motor parameters and operating voltage. However, it's essential to verify that the standard's recommendations align with the specific application and local regulations. Fourthly, consulting the motor manufacturer's data is highly recommended. Manufacturers often provide specific recommendations for conductor sizing based on their motor's design and performance characteristics. This information can be more tailored and accurate than generic tables or equations. Fifthly, conductor ampacity plays a vital role. The selected conductor must have sufficient ampacity to carry the motor's full load current continuously without exceeding its temperature rating. NEC Table 310.16 provides ampacity values for various conductor types and sizes. Sixthly, voltage drop considerations are crucial, especially for long conductor runs. Excessive voltage drop can negatively impact motor performance and efficiency. IEEE Standard 141 provides guidelines for calculating voltage drop and ensuring it remains within acceptable limits. Seventhly, short circuit protection is essential to protect the motor and conductors from fault currents. Fuses or circuit breakers must be properly sized to interrupt fault currents safely and quickly. NEC Article 430 provides detailed requirements for motor circuit protection. Eighthly, grounding is critical for electrical safety. The motor and its associated equipment must be properly grounded to provide a low impedance path for fault currents. NEC Article 250 provides comprehensive grounding requirements. Ninthly, ambient temperature in conductor derating must be considered. If the ambient temperature is higher than the value used in NEC Table 310.16, the conductor ampacity must be derated accordingly. NEC Table 310.15 provides derating factors for various ambient temperatures. Tenthly, conduit fill limitations must be observed. The number of conductors allowed in a conduit is limited to prevent overheating and ensure proper heat dissipation. NEC Chapter 9 provides conduit full tables and calculations. 11th, coordination with the local electrical inspector is highly recommended. The inspector can provide valuable guidance on local regulations and interpretations of the NEC. 12th, documentation is crucial. Maintain detailed records of all calculations, conductor selections, and protective device settings. This documentation will be invaluable for future maintenance and troubleshooting. 13th, regular inspections and maintenance are essential to ensure the continued safe and reliable operation of the motor and its associated electrical system. Check connections for tightness, inspect conductors for damage, and verify protective device settings. 14th, qualified personnel should perform all electrical work. Working with high voltage systems requires specialized knowledge and skills. Only qualified electricians and engineers should be involved in the installation, maintenance, and troubleshooting of motor circuits operating above 2300 volts. 15th, safety is paramount. Always follow proper safety procedures when working with electrical equipment. To energize circuits before working on them, use appropriate personal protective equipment, and follow lockout-tagout procedures. 16th, consider the motor's starting method. Different starting methods, such as across the line, reduced voltage, or solid-state starters, will affect the inrush current and conductor sizing requirements. 17th, harmonic distortion can be a concern in motor circuits, especially those with variable frequency drives. Harmonics can increase conductor heating and reduce equipment life. Consider using harmonic filters or reactors to mitigate harmonic distortion. 18th, power factor correction can improve system efficiency and reduce energy costs. Capacitors can be used to improve the power factor of motor circuits. 19th, surge protection can protect the motor and its associated equipment from voltage surges caused by lightning or switching transients. Surge protective devices should be installed at the service entrance and at the motor. 20th, insulation coordination is important to ensure that the insulation levels of all equipment in the motor circuit are properly coordinated to withstand transient voltages. 21st, consider the motor's duty cycle. Motors that operate intermittently or have frequent starts and stops will have different conductor sizing requirements than motors that operate continuously. 22nd, the use of shielded cables can reduce electromagnetic interference and improve system performance. Shielded cables are especially important in sensitive electronic environments. 23rd, proper cable termination techniques are essential to ensure reliable connections and prevent overheating. Use appropriate crimping tools and connectors. 24th, consider the use of cable trays or ladders to support and organize conductors. Cable trays and ladders can improve airflow and make it easier to install and maintain conductors. 25th, ensure that all equipment is properly labeled and identified. This will make it easier to troubleshoot problems and perform maintenance. 26th, keep accurate records of all equipment and their settings. This will be invaluable for future reference. 27th, regularly review and update your electrical system documentation to reflect any changes or modifications. 28th, stay up to date on the latest codes and standards. The electrical industry is constantly evolving, so it's important to stay informed about the latest changes. 29th, attend training courses and seminars to improve your knowledge and skills. There are many excellent training opportunities available for electrical professionals. 30th, network with other electrical professionals. Sharing knowledge and experiences can be invaluable. 31st, always prioritize safety. Electrical work can be dangerous, so it's important to follow proper safety procedures and take precautions. 32nd, never take shortcuts. Always do the job right the first time. 33rd, double check your work. Make sure that everything is installed correctly and that all connections are tight. 34th, test your work. Verify that the system is operating properly before putting it into service. 35th, document your work. Keep accurate records of all work performed. 36th, follow up. Check back with the customer to make sure that they are satisfied with the work. 37th, be professional. Treat your customers with respect and provide them with excellent service. 38th, be reliable. Show up on time and complete the work as promised. 39th, be honest. Always be truthful with your customers. 40thly, be fair. Charge a fair price for your services. 41st, be ethical. Conduct your business with integrity. 42nd, be responsible. Take responsibility for your actions. 43rd, be accountable. Be accountable for your work. 44th, be committed. Be committed to providing excellent service. 45th, be passionate. Be passionate about your work. 46th, be knowledgeable. Be knowledgeable about your trade. 47th, be skilled. Be skilled in your trade. 48th, be experienced. Be experienced in your trade. 49th, be confident. Be confident in your abilities. 50thly, be successful. Be successful in your career. When sizing conductors for motors operating above 2300 volts, remember that the NEC provides limited direct guidance. Instead, rely on a combination of factors. Firstly, consult IEEE Standard 141 for recommended practices on electric power distribution in industrial plants. This standard offers valuable tables and equations for calculating minimum motor amps for voltages up to 34.5 kV, providing a solid foundation for your calculations. Secondly, always refer to the motor manufacturer's data. This is a crucial step, as manufacturers typically provide specific amperage values for their motors at various operating voltages. This information is often more precise than generic tables and should be prioritized. Thirdly, engage a qualified electrical engineer. Their expertise is invaluable, especially when dealing with high voltage systems. They can provide tailored guidance based on the specific motor installation conditions and local regulations, ensuring a safe and compliant design. Fourthly, consider the motor's full load amps, voltage rating, and horsepower. These parameters are essential for determining the appropriate conductor size. The full load amps, in particular, will dictate the minimum ampacity the conductors must handle. Fifthly, pay close attention to voltage drop. Excessive voltage drop can negatively impact motor performance and efficiency. IEEE Standard 141 offers guidelines for calculating and mitigating voltage drop, ensuring that the motor receives adequate voltage under load. Sixthly, remember to factor in ambient temperature and conductor rating. High ambient temperatures can reduce the ampacity of conductors, requiring larger sizes to compensate. Consult NEC Table 310.15 for dating factors based on ambient temperature. Seventhly, ensure adequate short-circuit protection. Properly sized fuses or circuit breakers are crucial for protecting the motor and conductors from fault currents. NEC Article 430 provides detailed requirements for motor circuit protection. Eighthly, proper grounding is paramount for electrical safety. The motor and associated equipment must be effectively grounded to provide a low impedance path for fault currents. NEC Article 250 outlines comprehensive grounding requirements. Ninthly, consider the motor starting method. Different starting methods, such as across-the-line, reduced voltage, or solid-state starters, can significantly impact the inrush current and conductor sizing requirements. Tenthly, always prioritize safety. High-voltage systems demand strict adherence to safety procedures. De-energize circuits before working on them, use appropriate personal protective equipment, and follow lockout-tagout procedures meticulously. 11thly, maintain thorough documentation. Keep detailed records of all calculations, conductor selections, protective device settings, and any other relevant information. This documentation will be invaluable for future maintenance, troubleshooting, and inspections. 12thly, stay updated with the latest codes and standards. The electrical industry is constantly evolving, so it's crucial to stay informed about any changes or updates to relevant codes and standards. 13thly, consult with local electrical inspectors. They can provide valuable insights into local regulations and interpretations of the NEC, ensuring compliance with all applicable requirements. 14thly, perform regular inspections and maintenance. Regular inspections can help identify potential problems early on, preventing costly downtime and ensuring the continued safe and reliable operation of the motor and its associated electrical system. 15thly, ensure that all electrical work is performed by qualified personnel. High voltage systems require specialist knowledge and skills, so it's essential to use qualified electricians and engineers for all installation, maintenance, and repair work. By following these guidelines and exercising due diligence, you can ensure that motor conductors operating above 2300 volts are properly sized, safe, and reliable.